Dominic, thank you very much for your so kind introduction. I would like to thank very sincerely the organizers of the conference for the invitation. Moreover, I would like to express my deep gratitude to my colleagues cooperating with me on the topic of the talk, in particular Shoma Dutta, Andrzej Jankowski, Dominik Ślęzak, and others. So in my talk, I would like mostly to concentrate on future of RAF sets in the context of intelligent systems. And the main idea is that there is a need for developing of new computing model, and this new computing model is proposed on interactive granular computing. So I will explain what is this interactive, especially before granular computing, and I will start from some preliminaries about information systems, RAF sets, granular computing, and next I will give the outline about interactive granular computing and some comments about RAF sets in intelligent systems on the basis of this interactive granular computing. Let me start from this citation, which is a bit changed because this was formulated originally for biology, but this is true for intelligent systems. And we can read that tomorrow, I believe, we will use intelligent systems to support our decisions in defining our research strategy and specific aim, in managing our experiments, in collecting our results, interpreting our data, in incorporating the findings of others, in disseminating our observations, in extending or generalizing our experimental observations through exploratory discovery modeling in directions completely unanticipated. And you can ask if we have the relevant computing model for dealing with such problems, and also with problems which are related to cyber physical systems, the Internet of Things, Wisdom Web, Society 5.0, and so on. One very important issue I would like to emphasize is that in these considerations, aspects of perceptions and action cannot be omitted. And recently, there is also a discussion about modification of the Turing test. And as you can see, the Turing test, as originally conceived, focused on language and reasoning, and problems of perception and action were conspicuously absent. And so the discussion here is how to link this separated research on these issues related to reasoning, perception, and action. So in general, we should have in intelligent systems tools supporting decision making are based on construction of objects on which computations are performed, and we need a reasoning mechanism about such computations. So I will talk about two approaches. One which is mainly based on granular computing, and this is based on modeling in abstract space, and interactive granular computing is based on modeling in abstract and physical space. So I will start from preliminaries very briefly about RAF sets and granular computing. So granular computing was started by Professor Lotfi Zadeh and he was writing that information granulation plays a key role in implementations of the strategy of divide and conquer in human problem solving. So this is a very important observation. And roughly speaking, what we have in granular computing, we start from some atomic granules, which can be crisp neighborhoods, families of such neighborhood, fuzzy neighborhoods, and we have some aggregation operations. Using them, we can create more compound granules. We can have also some decomposition operations which can degranulate, in a sense, of constructed so far granules. So in rough sets, we will talk about these rough granules, and we will say what are the elementary granules, what are definable granules, and how we approximate granules. So the very basic notion of in rough sets is information systems, as we know. So this is similar as, for example, training samples in machine learning. So we have these tables. Rows are labeled by objects and columns are labeled by attributes. And on the intersection of columns and rows, we have the value attributes for a particular object. It is important to note that we are not asking where are and what are these objects which are in the first column, but we will talk about this also later. And what is now the basic concept? The basic concept is the information which we have about the objects. This inf with subscript A. A is a set of all these attributes for the object X. And the semantics of this is that the elementary neighborhood of X, it means the set of all objects which have the same information. So this is the idea on which was based the very first definition by Professor Pawlak of indiscernibility relation relative to a set of attributes. Two objects are indiscernible if and only if this information or signatures of objects relative to A are the same. Of course, this relation is a equivalence relation and creates a partition of the universe of objects which we have in this table. Later on, this relation was changed to tolerance or similarity, and many different generalizations of rough sets were introduced. So we have here this very basic granule. This is this equivalence class of object X, and now, if you would like to talk about aggregation in rough sets, they are called definable granules, say, and these are the unions of equivalence classes. And here we can see the very basic definition of the lower approximation and upper approximation and the boundary region. The lower approximation is a union for of a given set of objects. This set X is the union of all indiscernibility classes which are included in the set, and the upper approximation is the union of all indiscernibility classes which have non-empty intersection with the set X. And important concept is also the boundary region. This is the difference between the upper and lower approximation. And now we can say that if this boundary region is empty, we can talk about the crisp set. The X is a crisp set relative to a given set of attributes B, and if this boundary region is not empty, we can say that X is a rough set. So these are the very basic, very initial definitions of introduced by Professor Pawlak. Here you have this picture with Professor Pawlak giving a lecture in one of the first conference on rough sets. This was conference in Banff in Canada in '93, as you can see here. And now here I'm presenting the screen from this rough set database systems, where you can find that they have information about almost 40,000 papers related to rough sets. So this is the current situation, and during this 40 years, the relationships of rough sets with many other approaches were developed. In particular, some discussions about rough sets and vague concepts in philosophy, fuzzy sets, especially Dempster-Shafer theory, Boolean reasoning, and so on. I will say a few words about the Boolean reasoning a little bit later. And also, I have already mentioned that a lot of generalizations were introduced. You can find the discussions about them in Handbook of Computational Intelligence. Here is a quite long list of generalizations of rough sets. So, 2 words about relationships of rough sets with Boolean reasoning. This is very important, and also in some sense it was an independent development of in a sense parallel by the group working on a logical approach to data analysis in Rutgers University, started by Professor Hammer. She unfortunately died in an accident. But the very basic idea is coming from George Boole, and he was saying that to solve the problem P is necessary to encode properly this problem as a Boolean function, with this property that if you have the, say, Boolean processor computing this, what we know very well, what are the prime implicants. So by simple interpretation of this prime implicants, you can obtain the solutions for the problem P. And this is working very well for different basic concepts related to rough sets. Here are some examples. We can compute using this idea. We can develop algorithms for computing different kinds of reducts in information systems. Reducts were mentioned by Dominic during the introductions. Decision reducts, local reducts relative to objects, but also we can deal with discretization of symbolic value grouping. These methods were especially developed by Professor Hung-Sung Nguyen. Approximate reducts and association rules, these links also were developed by in his work. So this Boolean reasoning is working because discernibility constraints to be preserved during the, for example, reduction can be encoded by means of Boolean functions relevant to Boolean reasoning. And also it's important to note that during these 40 years, the combinations of rough set approach with other approaches were developed, especially with fuzzy sets. But here you can see a lot of other, like neural networks, genetic algorithms, granular computing, and so on. And especially I would like to emphasize combination of rough sets with fuzzy sets. And here this works on foundations, and many applications were developed in different groups. Yesterday, we have had a very nice talk by Professor Chris Cornelis. I would like to mention also the results of the group of Professor Sankar Pal from Indian Statistical Institute, where they obtained very many results, especially related to applications. So there is a lot of work on applications in different domains of RAF sets. Here I would like to mention also this what recently I have observed, that also we can talk about something like RAF-set-based approximation in optimization of complex granule construction. And this is also one of the direction recently, very recently emerging, at least in this, around these people with whom I have contact. And I would like to mention also one application which we call ontology approximation, which was used in our group dealing with several real-life projects. So in this case, this is something like this, just through the discussion with the domain expert, the system is able to, we are able to transfer knowledge from expert from domain expert to the system. And having this ontology, this is a kind of the, these are the kind of the hints along of this ontology, the approximation of this ontology in bottom-up, using bottom-up strategy is constructed, starting from the lower level, and gradually we are moving to the upper levels. So here are some pictures from this real-life projects, and maybe I will only mention the names. And here was one of the very first our experience with the project related to control of unmanned helicopter. And here you can see the video from the situation on the road. And all these problems related to, in fact, hierarchical learning was related to complex vague concepts. And the example of the complex vague concept is here, that we would like to develop a system which automatically will recognize from video if the situation on the road is safe. So this complex vague concept is a safe situation. And here is a picture related to the medical problem. This is emergency room for newborn children with respiratory failure. So this little child is here in this emergency room for at least several weeks, and with a lot of treatments and respiratory machines. And the problem was like this, that they have, it was a project with Polish-American clinic in Krakow. They have collected histories of these little patients, several hundreds, and the question formulated by medical doctors were like this, that can you, on the basis of the history of the patient and current state, predict if there is a high risk of losing life, if there is a danger, very high danger of losing life by this child, and maybe you can switch the alarm. So this will help us, because of course they have not one child but quite many. in such emergency room. And the next question is if we will be able to predict short-term therapy. So in this situation, and also in the previous, very important was to obtain from domain expert this ontology of concepts and to approximate this very complex, vague concepts, this very high risk of losing life. So here are some other projects related to, for example, algorithmic trading, satellite image recognition, on which was working Professor Hung-Son Nguyen with, in cooperation with scientists from Great Britain and NASA, and also the project related to support for commander of fire brigade. So I will not go maybe to the details now, but in general, this was a question if we are moving to approximation of the complex vague concepts. So this idea of using this methodology for ontology approximations was very helpful. We have obtained the classifiers which were, for example, stable on the robust with respect to changing of the situation and so on. So in general, I would like to also add some comments that in this hierarchical structures, say from the logical point of view, we can describe the situation in this way that we have several levels, of course, and on each level we are dealing with, for example, on the level I, we have some structures which in logic are called models or relational structures, and we have some language for expressing properties of these structures, and we have some satisfiability relation. But so the granules which we are obtaining here are they have the syntax from this language, and the semantics is a set of all structures which are on which this formula is satisfied, or where this or is true. And the main difference between this what we have in this approach and in the logic is that these structures and the language and also this satisfiability relation are not given, and they should be somehow learned from the data. So but if we are considering this kind of scheme, still you can see that this can be treated as a pure mathematical model, pure mathematical objects, not interacting with this what is outside, with the physical world, which may be represented by these arrows. But now I would like to say about this what was very interesting always for Professor Pawlak. He was asking what next, what next. So if we move to intelligent system dealing with complex phenomena, we can ask if this approach will be satisfied. We have big data generated by complex phenomena, and we cannot omit issues related to perception and action. We have here a lot of challenges, but from the point of view of RSTA's, of this very basic structure information system, we are moving to networks of information systems, and we, instead of static objects, we have dynamic objects, and we cannot omit interactions with the physical world, including humans. So just the literature about perception is very huge, but there is a very nice idea presented in this book, Action in Perception. So I would like to cite this. So the main idea of this book is that perceiving is a way of acting. It is something we do. Think of a blind person tapping his or her way around a cluttered space, perceiving that space by touch, not at once, but through time, by skillful probing and movement. This is or ought to be our paradigm of what perceiving is. I would like to add also some comment related to philosophy, and this is related to phenomenology originated by Edmund Husserl. And Husserl was frustrated by the idea that science and mathematics were increasingly conducted on an abstract plane, as he was saying, treating nature itself as a mathematical manifold that was disconnected from human experience and human understanding, independently of question of truth and applicability. He felt that the sciences increasingly dealt with idealized entities and internal abstractions, a world apart from the concrete phenomena of daily life. Here I'm citing again this discussion about Turing test, so I will omit this, but let us stop here for a moment, because if these intelligent systems are dealing with complex phenomena, so we should remember that in the complex systems, the elements are difficult to separate. And that this difficulty arises from the interactions between elements, that without interactions, element can be separated, but when interactions are relevant, elements co-determine their future state. Thus, the future state of an element cannot be determined in isolation, as it co-depends on the state of other elements precisely of those interacting with it. So the consequences of this are really very important. And for example, here is a citation formulated by Frederick Brooks. He was receiving the Turing Award for his research in software engineering. And he observed that mathematics and physical sciences made great strides for 3 centuries by constructing simplified models of complex phenomena, deriving properties from the models and verifying those properties experimentally. This worked because the complexities, these details ignored in the models, were not essential properties of the phenomena. However, it does not work when the complexities are the essence. So this is the very important observation. And in the relation to this, we can see that there are some very fundamental questions. Here is, for example, the questions formulated by Yuri Gurevich, working on the mainly on theoretical foundations, but he formulated 2 questions. The 2 main problems of computer science are what is a state and what is a transition relation. For the first moment, you can treat this as a joke, but if you move to this idea of intelligent systems dealing with complex phenomena, and if you ask what is the state of this phenomena in the real world and what is the transition relation, you will see that this is really the great problem. And also, people recognize, for example, people working with quantum computations, that it seems that we have no choice but to recognize the dependence of our mathematical knowledge on physics. And that being so, it's a time to abandon the classical view of computation as purely logical notion, independent of that of computation as a physical processes. So here is also this observation that dealing with this intelligent systems and basing this on the traditional abstract model of computations maybe not enough. And also, strangely enough, Vladimir Vapnik, in this very well-known monography about statistical learning theory in epilogue, is saying that constructing the physical part of the theory and unifying it with the mathematical part should be considered as one of the main goals of statistical learning theory. So, people working with complex systems are recognizing that these interactions, but the interactions you should really remember that these interactions are interactions between physical objects in the real world, and this is what we are perceiving and creating these models. These are some our imagination about these real interactions, and this understanding what are the interactions and how to treat them is a critical issue in understanding of complex systems of any sorts. So, and also, if you look on all this, there is another problem recognized by another very well-known scientist, Leslie Valiant, who also received Turing Award, that he's saying that this traditional algorithms are not proper for dealing with this problem we are discussing. He's saying that unlike most algorithms, this algorithm, which he's calling algorithms, they can be run in environments unknown to the designer, and they learn by interacting with the environment how to act effectively in it. After sufficient interaction, they will have expertise not provided by the designer, but extracted from the environment. So it is important that contrary to the traditional algorithmic, this algorithm which we are designing is for the designer, this function computed by the algorithm is not known in advance a priori. Yes, it's necessary to learn. Yes. So now we are going to this idea that if we, what we can do in this situation. The one only possibility I can see is that we should have a continuous connection with these abstract models and real world, and through this continuous interactions we can try to build models and modify them to trying to solve and to support the decision processes. And along this line, again, I am citing the Leslie Valiant, who on his webpage was writing something like this, that a fundamental question for artificial intelligence is to characterize the computational building blocks that are necessary for cognition. And so these computational building blocks are granules, but these granules are more general than these granules which are in granular computing, because talking about the cognition, you cannot omit aspects of perception, but you cannot talk about perception without talking about physical objects. So in this case, we have this more complex granules, and in fact, this is what we are trying to develop, this idea of interactive granular computing, So this is something like this, that we can take this granular computing and we can somehow model also interactions with the physical world, and over this we have kind of the reasoning which is which is much more advanced, I will say, than we use so far in mathematical logic or in applications. So our assumption is that we have physical objects which are existing in the physical space and are embedded into its parts. And these physical objects are interacting in the physical space, and thus some collections of physical objects may create a kind of the dynamical systems in the physical space. And now, if you have physical objects outside of the abstract space, so you have several questions how to generate the relevant configurations of physical objects and modify interactions between them, how to perceive of this object and their interactions, means where, how, when, and what really we should perceive. And also is important that perceived properties should be in a sense robust, at least to as high as possible degree with respect to unpredictable interactions from the environment. So with all of this, we are trying to extend this granular computing by this possibility of interacting with the physical world. So we don't like to close everything, as Husserl was saying, in mathematical manifold, because it is not possible, because otherwise we are separated from the real world. And so the question is how to define these very basic objects, which we call complex granule or C granules for short. And a special kind of these IC granules are informational granules. There is another issue which was discussed in for years, for example, in psychology, was a symbol grounding problem, for example, how it is possible that we can somehow link abstract objects with the physical objects. So there are quite serious problems here which is necessary to overcome. And now a very important issue is what is the control of this C granules, which is just a mechanism describing the behavior of this C granules. So I will only very shortly discuss, for example, this idea of C granule with control. The outline of the general procedure of computation in interactive granular computing is realized by control of C granules based on searching for relevant transformation of information granules and their implementation. So here is a very intuitive explanation that in this complex granules we have these two layers, informational layer and physical layer, and somehow this informational layer where we can have this abstract objects are linked with a physical layer, but we can say physical pointers, or this is what we are calling informational granules or IC granules. And this control of such a granule, of course, if it is not non-empty, say, control, is able to initiate communications between informational layer and physical layer using relevant IC granules. allowing to collect in informational layers properties of perceived physical objects and their interactions. And important role in this is playing this what I am calling here implementational module. So the situation like this, that if in this informational layer, control is, for example, deciding that it's necessary to maybe open or generate a new IC granules, the specification of this task is formulated here and is submitted to this implementational module. And this implementational module may reply with two decisions. One decision is that this is maybe too hard for me, and you should decompose this into the maybe plan or maybe a kind of the linear plan or concurrent plan or something like this, or is able to directly implement this, and in this case is creating this link. What is important here is that this IC granules have ability to encode information in the physical objects and decode of properties of physical objects into this informational layer, of course, if these objects are so to say sufficiently close to the scope of this granule. But it is also important to note that in this informational layer, control can have some domain basis or physical laws, and having information about created structure of this pointer or this IC granule, and using this domain knowledge or physical laws can infer properties which are in this physical layer, maybe far away from this control. So these are these issues which I'm discussing here. For example, here is a very basic cycle. In this very basic cycle is based on this assumption that there is a kind of the database of rules on the basis of which this control of C granule is selecting rules which are which have on the left hand side some conditions, and on the right hand side they have specification of transformations of this IC granules. And if the selection of the rule is possible, so implementation of the selected transformation is activated, and the information about the currently perceived situation is updated. Okay, and if this selection of the rule is not possible, so in this case, for example, depending on understanding of the currently perceived situation, we can use maybe domain knowledge trying to extend the knowledge about the currently perceived situation. So this is this kind of the very basic thing. So there's a lot of issues related to this to this granules. I see that my time is coming to the end, so I would like to maybe say a few words only about this control, because when we talk about this control of C granules, so there are a lot of issues. I mentioned only really very little, but you can have this set of rules, how these rules are can be learned as adaptive strategies, specification of generic granules, decomposition strategies, learning strategies, and so on. And here is a scheme representing this complex C granule, where we have this physical pointers and this IC granules generated by the control, and this informational layer, we have this abstract information where in the say in the spatiotemporal specification of to spatiotemporal specification of windows corresponding to the parts of physical space which we are perceiving is labeled by information which was possible to obtain. And next, these informations can be aggregated, so these triangles represent these hierarchical processes, and they can create this computational building blocks for cognition, which were mentioned as granules by Professor Leslie Valiant. So this is a kind of the scheme here is a kind of another vision of this more complex granules. Another very important issue that having these complex granules, we should have the proper mechanism for reasoning about these granules and computation over them. So reasoning judgment is really realized over this interactive computation supporting realization of perception. We understood this as understanding the perceived situation to satisfactory degree for making the right decisions. So the general change of the situation which we have now comparing this previous scheme which was related to this hierarchical learning is that this structure is in continuous interaction with the real world, with the environment, and judgment should support in continuous interaction with the physical world, discovery of relevant structure and computation and building blocks over them for cognition. And related to this reasoning is really a lot of challenges from the logical point of view. And also Leslie Valiant is saying that a specific challenge is to build the success of machine learning so as to cover broader issues in artificial intelligence. And this requires in particular a reconciliation between two contradictory characteristics, the apparent logical nature of reasoning and the statistical nature of learning. So it's a lot of very interesting issues related to this reasoning. So this is not only deduction, induction, and abduction, but also we should have in mind that we have these issues related to experience, explanation of behavior, and some other things which are discussed by people from philosophy of logic. And also, if you would like to cover practical judgment, we can use this citation that practical judgment is not algebraic calculation. Prior to any deductive or inductive reckoning, the judge is involved in selecting objects and relationships for attention and assessing their interactions, identifying things of importance from potentially endless pool of candidates, assessing their relative significance and evaluating their relationships well beyond the jurisdiction of reason. This is also also important to note that we can have a very nice link with the idea of computing with words by Lotfi Zadek. I have no time to discuss this, and also with this observation by Yuda Pirl. Also, she received the Turing Award, and he's saying that the causal inference requires two additional ingredients: a science-friendly language for articulating causal knowledge, for example, a fragment of natural language, and a mathematical machinery for processing knowledge, combining it with data and drawing new conclusions about the phenomenon. So these are, and also this is also related to this the research and the conclusions formulated by Professor Melanie Mitchell, working for many years in Santa Fe Institute. and related to these issues which are related to abstractions and analogies. And she's saying that these problems remain completely open. And I think that here we need to base all this research on solid foundations. So what I am saying is something like this, that nowadays we can have a lot of evidence in many branches like multi-agent systems, robotics, cognitive science, and so on and so on. And unfortunately, this research, as I was saying, is separated, like perception and actions and the reasoning. And for having some good foundations for developing intelligent systems, especially dealing with complex phenomena, we should have a good computing model. And this interactive granular computing, I think, are also important for many different areas. And let me finish with some comments related to rough sets. We started from this very simple object, mathematical object, like a data table or information systems. But when we ask what we have in this first column, these objects, in case of intelligent systems, we should consider this in the broader context, in the wider context, in the context of this kind of the complex granules. And here we have this control, which is creating this IC granules for making the links with the abstract, with physical space, and this abstract space, in this case, reduced to the information system. So traditional approach to rough sets was like this, that we have this abstract space where we have this information or decision systems, and this is just separated from the physical world. And unfortunately, in the case of this rough sets, which we would like to consider in interactive granular computing, we have these information systems linked with the physical world through these IC granules. And in this case, we have this very also complex problem of dealing with objects which are not purely mathematical, because we should have the objects which are able to link abstract and physical objects. And the same situation is with the fuzzy membership function. In the fuzzy set theory, we start from this, we have this fuzzy membership function defined on the set of objects into, for example, interval 0, 1, but this kind of the function is a pure mathematical object, just not related to the physical world. But for the issues related to this complex phenomena, we would like, for example, to estimate the risk of the changes of the, for example, some values of some currencies in the financial market, but not related to the fixed set of attributes or objects, but we should allow to have, in a sense, continuous interaction of this abstract space with the physical space, trying to search where, when, what, and how we are able to obtain data on the basis of which we can create, try to create these proper models. So there are other important aspects, and now towards of the summary, I outlined some aspects of the perceptual rough set approach. And now we are in the situation, here you have see a Professor Pawlak with a lecture, what are rough sets? And again, this question moved on this higher level is that the rough set should be considered in dynamic space of reasoning constructions, and this are not purely mathematical as the basis for complex classification approximation. So this is something what is really fascinating, and we discuss this interactive granular computing model as a base for design intelligent system dealing with complex phenomena. And the aim was to explain also how this interactive granular computing has the potential to handle the grounding problem by bridging a connection between the abstract mathematical modeling and real semantics. Yes. Oops. And here are some links to the papers, which you can find, for example, in DBLP. And also, I would like to mention the paper in the proceedings with Dominic, and where are really discussed this path on which we are currently moving from the information systems to intelligent information systems, and in this paper you can find a lot of other evidence that we have really in very many domains this evidence calling for the need to create the proper computational model for intelligent systems, especially when they are dealing with complex phenomena, but this is more and more important. Thank you very much for your attention.
Andrzej, if you allow me, I would have a question.
Yes.
Because you mentioned about these two aspects of interaction when you were showing these hierarchical systems.
Yes.
One aspect was related to interaction between information systems at particular levels of hierarchy.
Mm-hmm.
And another aspect was related to their interaction with physical world. So these two
yes.
types of interaction should coexist. I would like to ask you about, is it possible also to model some distributed modeling or distributed computations using these interactions?
Yes, of course. This is very important question, because mainly I was able to outline this idea of complex granule very shortly, but you can consider also the situation that you have society of the C granules, and this C granules can have, you can have a situation that there is a kind of the central control for granule forces society, but you can have also the situation that you have this control is distributed among all these C granules, and you have here the link again to this huge area of research of people working on self-organization, for example, and of course this is possible to also model a distributed system in this way. For example, we can have this kind of the situation that we have some granules and some elementary interactions which are defined, and we are looking for some other elementary granules and with some interactions between them in such a way that there's together this society of C granules, which can be treated as a meta, say, complex granule, the pattern of behavior of this complex C granules has required properties. so this can be related to discovery of materials or medicine or maybe some other issues. So I think that what is important that we can have nowadays we have very many so to say different domains of activities related to different aspects, but slowly I think this material and this evidence we have from these very many areas which I mentioned require to have some basic say foundations and basic ideas for modeling, so that the people working in different areas will not talk about in fact the same, developing different languages and so on. So definitely it is possible to talk about also and this is a very important issue about this distributed control and distributed systems.
Hello, do you hear me?
Yes, we can.
Okay, so
but we cannot see you.
I'm sorry, I don't know how to switch on my video, but I don't know what would happen. Okay, so my question is related to the problem of judgment. You mentioned about judgment in in few situations, but I would like to ask about so what type of judgment you can expect instead of the traditional, when you have to ask the expert about for example, you ask some annotators to assign some decision value to some objects, or you ask the observers to give some.
This is very important. Yeah. Also, of course, in just to give a kind of the maybe example, I can say that such systems should also have ability to interact with such physical objects like humans. Yes, and for example, human experts or team of experts, medical experts, and just analyzing the particular case, this system can send a query to this expert team asking for advice what to do and what is the opinion of this team. So here's again this judgment will be encoded in natural language, because these medical experts will use this judgment in natural language, and the system should be able to somehow link this opinion with the current perception of the situation of a given patient. So this is very important if we are trying to move, for example, from the as the people are nowadays start to say that we should move from the kind of the statistical medical decision support to personal medical support systems. Okay, so this judgment is just related. For example, this can be also another example. We can have, for example, a huge database, knowledge database about some kind of illnesses. And when we are perceiving the current situation, this system can communicate with this knowledge base and is trying to extract the proper piece of this knowledge from this knowledge base such that together with this piece of knowledge he can extend understanding of this case. So this is again another possibility of this judgment. And now just talking about this, I was mentioned also this professor Melanie Mitchell, and she was saying that this most important step, which we are not, which is not possible yet to to deal properly, is that in the humans in the situation when is, as she was saying, unbounded or endless pool of possibilities for different decision, this expert people are able to select very often the proper path. Yes, so this we need this dialogue with human experts, and we cannot omit. And also many people also recognize this necessity. They were using, for example, the name of Wisdom Web, where we can connect internet with a lot of things, a lot of physical objects, but also with humans, just to create this kind of the environment in which we can solve the problems. So this is what I can say at the moment. I don't know if this is what you expected.
It was really great to listen to your talk today. So all of us send best greetings to Warsaw.
Thank you very much for attending, for your patience, and I think that there is something what will grow in the future, but it is necessary to have a lot of work still. Thank you very much.